The science of strong roads. Have you ever wondered what makes a road last for years, carrying heavy trucks and cars without falling apart? It's not just about the surface you see. There's a whole world of science happening underneath your tires. Hello, science fans. I'm Dr. Amina Bello, and I'm excited to take you behind the scenes of road construction. Today, let's talk about something you drive over every day, the ground beneath our roads. It's easy to overlook, but it's the real hero of every highway and street. Why is a highway smooth and strong, but a dirt path gets muddy and rutted after just a little rain? What's the difference between a bumpy country lane and a superhighway? The secret is in the soil underneath. The ground below the pavement is carefully engineered to handle all that weight and weather. Engineers must turn ordinary, crumbly dirt into a foundation that supports thousands of vehicles every day, in all kinds of weather. If the soil is weak, roads crack, sink, and develop potholes. That's why you sometimes see bumpy roads after heavy rains or floods. So, engineers use science to make the soil dense and stable. They test, measure, and improve the ground before any asphalt is poured. This is a key part of civil engineering. It's where geology, physics, and engineering all come together to build something strong and lasting. How do they do it? With a compaction test, a scientific way to find the perfect recipe for strong soil. This test helps engineers know exactly how to prepare the ground. The secret ingredient? Water, but just the right amount. Water helps soil particles stick together, but too much or too little can cause big problems. Too little or too much water weakens the soil, making it unstable and unsafe for building roads. The compaction test finds the just right amount, so the soil is strong, stable, and ready for anything. Join me as we explore how compacting soil keeps our roads strong and safe, and why this step is so important for every road you travel. By the end, you'll see that building a great road is an amazing feat of science and engineering, one that starts from the ground up. Let's take a closer look at a handful of dirt. At first glance, it might seem simple, just some earth scooped up from the ground. But there's a lot more going on beneath the surface than you might think. Soil is made up of tiny particles, but it's also full of empty spaces, voids that are filled with air and water. These spaces are crucial because they affect how the soil behaves when we build on it. If you try to build on loose, unprepared soil, the weight of heavy loads, like buildings or roads, squeezes out the air and water from those spaces. As a result, the ground sinks or shifts over time. This process is called settlement, and it can cause big problems. Uneven settlement leads to cracked, bumpy roads, potholes, and expensive repairs. It can even make roads unsafe for drivers and pedestrians. That's why we use compaction. Machines squeeze the soil particles closer together before any construction begins. This process reduces the amount of air in the soil, making it much more stable. Think of it like packing a suitcase for a trip. If you just toss your clothes in, you run out of space quickly. But if you fold and press everything tightly, you can fit much more, and it all stays in place. Compaction does the same thing for soil. It packs the particles tightly together, making the ground firm and less likely to shift. When soil is denser, it's much stronger and can support more weight. This property is called shear strength, and it's essential for supporting roads, buildings, and bridges. Compacted soil is also less permeable, which means water can't easily flow through it. This helps prevent water from washing away the soil or damaging the road from underneath. Without proper compaction, roads would settle unevenly, crack, and need constant repair. Over time, this would cost a lot more money and create headaches for everyone who uses those roads. By compacting the soil, engineers create a strong, reliable foundation, one that's even better than what nature provides on its own. This careful preparation is a key part of every successful construction project. This step ensures our roads are safe, smooth, and durable for years to come, no matter how much traffic they carry or what the weather brings. It's a great example of how science and engineering work together to make our world better, safer, and more efficient. That's why soil compaction is absolutely essential for every road you travel on, whether it's a quiet street or a busy highway. Thanks to science and smart engineering, we can keep moving forward, safely and smoothly, every single day. How do engineers find the perfect soil recipe? With the standard Proctor compaction test, the goal: build a compaction curve showing how soil density changes as water is added. The test uses a standard mold, a special hammer, and precise water measurements. Soil from the site is dried, then mixed with a set amount of water. The damp soil is packed into the mold in 3 layers, each hammered 25 times. This simulates real-world compaction. The mold is filled, trimmed, and weighed to get the wet density. A sample is dried in an oven to find the moisture content. With these numbers, engineers calculate the dry density, how tightly the soil particles are packed. This process is repeated with more water each time. Each test gives a new point for the compaction curve. The curve reveals the best combination of water and compaction for strong soil. Let's run the test. Today, we're diving into the fascinating world of soil compaction, where numbers and science come together to build the roads we drive on every day. We start with soil at 6% moisture, carefully preparing and compacting it, then weighing the sample to see how much water it holds. Suppose the wet density is 114 pounds per cubic foot. This number tells us how heavy the soil is, including all the water inside. We dry a sample in the oven. If it loses 5.7 grams of water from 100 grams, that's 6% moisture, right on target. This step is crucial for understanding how much water was in the soil to begin with. To find dry density, we divide the wet density by 1 plus the moisture content in decimal form. This calculation helps us separate the weight of the soil from the weight of the water. So, 114 divided by 1.06 equals 107.5 pounds per cubic foot. That's the dry density, just the soil, no water. We plot this on our graph: 6% moisture, 107.5 dry density. Each point is a clue in our soil story. Next, we repeat the process with 9% moisture, carefully mixing in more water and compacting the soil again. This time, maybe we get a wet density of 122.5 pounds per cubic foot. The dry density now is 122.5 divided by 1.092, which equals 112.2 pounds per cubic foot. We record this new result. We keep testing at higher moisture levels: 12%, 15%, 18%, each time compacting, weighing, and plotting the results. Every test adds another piece to the puzzle. Each point on the graph shows how dry density changes as water increases, revealing the relationship between moisture and soil strength. The curve starts to take shape, showing us the sweet spot where the soil is strongest and most stable. This data helps engineers find the best moisture for maximum soil strength, ensuring the ground beneath our roads is solid and reliable. It's a numbers adventure that leads to safer, longer-lasting roads. Roads that can handle heavy traffic and all kinds of weather. Science in action right under your wheels. Every journey you take is supported by these careful calculations and tests. After testing, our graph is filled with data points. Connect the dots, and you get a bell-shaped compaction curve. At first, adding water increases dry density, soil packs tighter, but after a certain point, more water makes density drop. The peak of the curve is the maximum dry density, the tightest packing possible. In our example, that's 115 pounds per cubic foot. The moisture at this peak is the optimum moisture content, here 12.1%. This is the sweet spot for compaction. Just enough water for particles to slide and pack tightly. Too little or too much water, and the soil isn't as strong. These two numbers, maximum dry density and optimum moisture, are the keys to building strong roads. That's the result every engineer is after. Why does density rise, then fall as we add water? Dry soil has lots of friction. Particles resist packing. Add water, and it lubricates the particles, helping them pack tighter. But too much water fills the spaces between particles, and water can't be compressed. Now extra water holds particles apart, lowering dry density. The trick is to find the perfect balance, enough water to help, but not so much it gets in the way. That's why the optimum moisture content is so important. It's the science behind every strong road. The lab test sets the targets for real construction. Crews aim for 95% of the maximum dry density and the optimum moisture content. Water trucks spray soil to reach the right moisture, and heavy rollers compact it. Field tests, like the nuclear density gauge, check if the soil meets the standard. The gauge gives instant readings of density and moisture. If the soil isn't dense enough, more rolling is needed. This cycle continues until the whole roadbed meets the scientific standard. The result, a strong, stable foundation for the road. Science and engineering work together to make roads last. Every smooth drive starts with this process. From dirt to superhighway, the compaction test is science in action. It lets engineers turn loose soil into a strong, reliable foundation. Every smooth road owes its strength to this careful process. It prevents potholes, saves money, and keeps us safe. Even ordinary dirt holds amazing scientific secrets. By testing and measuring, we build things that last. The compaction curve is a blueprint for quality roads worldwide. Next time you travel, remember the science beneath your wheels. Building a better world truly starts from the ground up. Science is everywhere. Let's keep exploring.